So let's pick up right where we left off in the last video. So here are some code using functions that simulate behavior inside a drone. And you can add as many functions as you can. In the last video, we used the throttle, compute throttle function. We added the adjustMotor, read altitude, same principles, but different functions. So we're reading all these altitude, computing throttle, adjusting the motor. It works. You can add a lot of these functions, but as your system grows, this can be very messy. Every new feature becomes a new function, and every new sensor, every actuator, every check adds more floating logic. And soon your main function right here will become like a jungle. What we're missing here is something called structure. In this video, we'll take the next step toward building real systems. We're going from isolated functions to modular thinking, the way machines actually organize their thoughts. In the last video, we learned how machines act through functions. A function like adjustMotor or the compute throttle that we did in the last video. Read values, perform logic, and triggers behavior. That's how machines respond. Now imagine your machine isn't just reacting, it's sensing from multiple inputs, storing internal states, and reacting in combinations. One sensor might need to be calibrated, another needs to be reset. One motor might have an emergency override. Suddenly, managing everything with separate functions becomes fragile, unscalable, and even dangerous. Okay? So real machines don't work as random lists of functions. They work as modules, subsystems. Think about it like a brain's made of brains. And that's where we enter the world of objects. And in C++, the word we use to build those modules is class. Now, let's write our first class, and we're going to call it a sensor. And it's not going to be just a function, but a thinking unit with memory, logic, and identity. Okay, so step one, we pull in the IOStream library. We'll say include IOStream. And this gives us access to the cout, our voice to the screen, and that's how we see what's inside our code through the cout. And using name space standard. To keep things clean, we add using namespace. This way, standard. That way, we don't need to type, let's say, std cout, and then we call something. Instead, we're just going to say cout, okay? Just to keep things cleaner. And you'll see this shortcut in a lot of small or educational projects. Then we start with writing class, and then we'll give it a name, sensor. Okay, and as I mentioned, a class in C++ is how we group related data and functions into one unit. Instead of handling variables and behavior separately, we bundle them together into something that represent a real-world thing, like a sensor. You decide what it holds, what it can do, and how it should behave. It's not just a code. It's like a custom machine part designed in software. Okay, so next we write private. So here we define a private variable, and we're going to call it float. We're going to call it value. Okay, so private here means no one outside the class can access this directly. Why? Because internal data should be protected, just like a microcontroller protects its sensor pins. You don't want the outside code messing with the core readings. Only the class itself is allowed to update or access this safely. Okay? Because now, next we open the public section, and here we write public. Okay, and this is where we define the safe ways for other parts of the system to interact with this object. Think of this like a USB port or function buttons on a device. You're not you're not opening the machine, you're using its interface, okay? And this here we're going to add the first function inside the public, and it's going to be the read function. So void read float, give it value, variable, and inside we assign value to the new value. Okay, so this is our read function. It takes one input, new value, and the type of it is going to be a float. That could be any sensor data, like let's say 72.5, -3.2, or 0.0. Inside, we assign that to value, and that's it. Simple, clean, and safe. No direct access. The only way to update value is through this function. Okay, and notice here I mentioned void. So, what does that mean? Void means the function doesn't return anything. It's just perform an action, like pressing a button, or or like switching a relay. You're not asking for a result. You're causing a change. And in embedded systems, that's extremely common. And like I mentioned, like trigger a relay, or turning on an LED, send a command, reset a system. All of those are actions, not answers. So we use void in that case. Next, we create the second function, which is going to be the calibrate function. So we say void calibrate and inside we'll say value minus 0.5. So here the calibrate function is subtract 0.5 from the current value. And the reason I did this, in real systems, calibration is a key. Adjusting for offset, noise, or error. So this tiny simulation mirrors what embedded devices do all the time. Okay, so very simple, just for the sake of the example. And then the third function, finally we write the display function. So that would be void display, in a bracket, and then cout, and we say sensor value equal something like that, and then we add the value and we end the line. Okay, so finally we write the display function. This prints the internal value to the console, and as I mentioned, in real systems this would be literally the serial output, or telemetry transmission, or dashboard visualization. You can think about it like that. Okay, all right, so now what do we have? Well, we have internal memory, functions to receive input, adjust, and report. And this is now a complete machine module, small, self-contained, and reusable. So next, we're going to write the, as always, the int main function, the main function. So it'll be main. Okay, and then so here, this is where we simulate running our system, okay? And then we call the sensor, and then we give it an object. We call that sensory, or sensor, okay? So here we create an instance of the sensor, and that is called temperature sensor. Think of this like plugging in a real sensor to your embedded board. We're no longer looking at the class, the blueprint. We're building a working module, okay? And then next, we call the read function, right? So we say temp sensor, okay? And dot read, and then we give it a value, let's say 78.3. So here we call the read function to simulate reading a temperature, and that temperature would be 78.3 degrees, maybe from a room sensor or a thermistor, okay? So this updates the internal state of the object, and it is now holds that value, okay? So what's next? Well, next, we're going to calibrate that value, right? So we run the temp sensor, and we write dot calibrate, and you notice how calibrate comes out because it's part of the class and part of the object, and that's it. So here we run the calibrate function after the read. Basically, we took the value. Now the calibrate will simulate adjusting for offset, electrical noise, or sensor drift. These like small corrections are very important in robotics or medical devices or any other machines. So we took the value with the read function. Now we're going to calibrate it. So it's going to go to that function and calibrate it. And then lastly, we're going to do the display because we want to see our result. Display, and that's it. So finally, we call the display. This basically prints the final calibrated reading. In real system, this might go to a screen, or let's say UART output or telemetry packet, okay? And then, of course, lastly, we ended up with return 0, okay? So here I'm just saying, and now we finish with this, like the function completed, or a standard way of indicating that the program ended successfully, and goodbye, okay? And then we save that, and now we're gonna run it with E++, and then what's the name of the function? EP3 CPP so, and then all right, and then now we're gonna call all right. So we got the value as 77.8. So there it is, a machine component receiving an input, adjusting its internal state, and reporting data just like a real sensor. We've built and tested one sensor object, the temperature sensor, this one. But what happened when your system needs multiple sensors? Temperature, pressure, gyroscope, light, all working together. Well, this is where object-oriented design really shines. We don't have to copy and paste the same class that we just did right now, which we can do, but that's a lot of work, or that's a lot of writing. What we can do is we can reuse the class, the blueprint, and just create new objects. Each one behave like a separate machine with the same interface. So here we can just go below here and then write sensor. We call the blueprint and we say create gyroscope. Gyroscope sensor for me. Or let's just call it sensor. Okay. Here we create a second object. We called it gyrosensor. Same class, same rules that we did in temperature, but now it's a completely independent unit, just like adding another sensor to your embedded board. Okay. And then we can do the same thing. Now we call the gyrosensor to, we call the object to give us the read, calibrate, and display for a certain value that we pick. For example, we can say gyrosensor read, let's say 0.045, okay? And then also calibrate it, and then display it. That's very easy, right? All right, and that's it. Now we give gyrosensor its own reading, which is 0.045. Maybe that's angular velocity from a rotating motor, okay? Then we calibrate it, removing mechanical bias or drift or something, and then we display the result, just like we did in the temperature sensor. So we save it, and then here we just call function, and here we go. We have sensor value 0.4 minus 0.455. Okay, so two sensors, same design, different rules. This is how real systems scale. You build one clean module and reuse it for every part of your machine. And again, so this is if you are doing the same functions, but using it on a different sensors. But if you want to build a completely different logic for the, let's say, gyro sensor, you can do that. You can build another class for that. But if sometimes we have two sensors uses the same principles, same methods, whether reading, calibrating, displaying, might as well do this and build another object. Okay. So let's zoom out for a second and see why we're doing all this. Well, without objects, you will end up with dozens of random functions, while with the object with objects, you wrap behavior into clean, reusable class templates. Also, in the non-object world, your functions don't remember anything. But with objects, each instance tracks its own memory. It's like real sensor holding its last reading, okay? And also, spaghetti code is nearly impossible to debug, but objects are self-contained. You can isolate and test them like individual machine parts. And finally, I want to say scaling. With procedural code, every new feature adds chaos. With objects, you just make more instances, like plugging in more devices without rewriting your system. Okay, so this table isn't just about code. It's about how real machines are structured. If you want to build systems that are clean, reliable, and scalable, that's how you do it. And remember this, without objects, you get scattered functions, no memory, and chaos as the system grows. And with objects, you get structure, safety, and even scalability. In real systems, whether it's a drone or a smart thermostat or robotic machines, you need structure, not just for you to say, like, I want to build something organized, but for other engineers, for future you, and for the machine itself to scale without chaos. So let's try something interesting before we end this video. So here's something interesting. If we try to directly access the internal value of our sensor, which is basically in the private section called value, and its type is flow, and we'll say temp sensor dot value equal, and we'll give it like 99.9. Okay, so what do we have here? We just got an error. Interesting. Why? Well, because we said in the beginning, value is a private variable. So in the private section, and that is called encapsulation. Encapsulation means if you're not part of the object, you cannot access its core, or you cannot touch the core, the private variables. In hardware terms, this is like signal shielding. You don't let random wires poke into protected lines. You must go through the public section, interface, the official channel. This keeps the system clean, controlled, and even safe. Now you're starting to see it. In machines, everything is modular. Sensors read, controllers decide, and motors act. Each one is an object with its own data and its own logic. So when we define a class, we're defining the behavior of a real-world part. When we create an object, we're simulating a real module. This isn't just syntax, it's the architecture of modern machines. So, all right, so now I wanted to tell you that you just built the foundation of real embedded control software. Modular, reusable, rock-solid components. This is the stuff that runs inside drones, satellites, and even medical devices. And we're just getting started. In the next episode, we go deeper into the life cycle of objects. We'll talk about constructors and destructors and how modules power on, initialize, and safely shut down. And because in real systems, startup and shutdown logic is everything, especially when you're spinning motors, flying drones, or even reading brain signal. All right, I'll see you guys in the next video.